Hey everyone, this is Dr. Habib Ahmed. Welcome back to my channel. If you are working with semiconductor devices, you know how crucial it is to ensure low contact resistance for optimal performance. Today I'm going to walk you through the step-by-step process for measuring contact resistance using circular transmission line model or CTLM technique. The circular transmission line model technique is widely used to measure the contact resistance in semiconductor devices. It's really important to understand the CTLM structure. So, for example, here is the CTLM pattern. The CTLM structure consists of a series of concentric circular contacts on a semiconductor surface. The contacts are typically metal pads deposited on the semiconductor material. The spacing, or you can call it the distance between these contacts, varies, allowing you to measure resistance as a function of the spacing. So as you can see over here, the spacing over here can be like 5 micrometers, 10 micrometers, 15 micrometers, 20 micrometers, 25 micrometers, and 30 micrometers. Now, how do you make the patterns? The patterns can be made using fabrication of the CTLM patterns. And for that purpose, you need to perform photolithography. You use photolithography to pattern the circular contacts on the semiconductor and then perform metal deposition. You deposit metal contacts using techniques like thermal evaporation, sputtering, or E-beam evaporation. And then you remove the unwanted metal to leave behind only the circular contacts. After the CTLM structure is made, you need to perform current voltage measurements across these different patterns, in which you apply a voltage across two adjacent contacts. For example, you may apply one contact inside this circular pad, and you apply another contact over here. So you apply a voltage across two adjacent contacts and you measure the current across these contacts, and then you repeat the process for the rest of the contacts as well. Now here you can see the R1 over here represents the radius of the inner circle, and R2 here represents the radius of the outer circle. You might like to use a probing station equipped with micro probes to make the electrical contacts with the metal pads. For higher accuracy, use a 4-point probe configuration to eliminate the effects of lead and contact resistance in the measurements. Now, so you apply a voltage across these contacts and you measure the current. So as an example over here, I've got 5 different patterns. The spacing over here for this contact is 10 micrometers, 20 micrometers for this one, then 30 micrometers, then 40 micrometers, and then 50 micrometers. And for each of the spacings, I measure the IV characteristics. So for example, the current is going to be the highest for the smallest distance, or for the smallest spacings between these contacts. So for example, this contact over here is going to result in the red curve, the red IV characteristic. And by the way, this is a PTLM, which means that I applied the transmission line model for a P-type contact over here. And then the blue curve here corresponds to this 10 micrometer spacing. The green corresponds to 20 micrometers. This is 10 micrometers, this is 20 micrometers. Then the green one corresponds to 30 micrometer spacing. The brown one over here corresponds to 40 micrometer spacing, and finally the black curve over here corresponds to 50 micrometers spacings. So you perform the IV characteristics across these spacings, and then from the IV characteristics you measure the resistance for each of the patterns. So for example, how do you measure the resistance for this red curve? You have got the voltage in this case runs from approximately -4 to 4 volts, and similarly the current runs from 0.1 amps to -0.1 amps to 0.1 amps, or you can say the current runs from -100 milliamps to 100 milliamps. So you divide the change in voltage divided by the change in current, and this gives you the resistance. So for example, for the red curve, the change in voltage is 8 volts and the change in current is approximately 200 milliamps. So 8 divided by 0.2, it's going to give you the resistance for the red curve. And similarly, you measure resistances for the blue, green, brown, and the black curve as well. And after that, you plot these resistances either with the gap spacings, or you can also plot them versus the radii. So for example, in this case, we have fixed the outer radius to 200 micrometers for all the 5 cases, while the inner radius varies over here. Like this one has a radius of 190 micrometers, then this one has a radius of 180, 170, 160, and finally 150 micrometers radius. So you plot the resistance. So I've got 5 data points, and you measure these 5 different resistances, and you plot them versus the gap spacing. And after that, how do you extract the contact resistance? So the resistances over here, these data points actually correspond to the measured resistance. We actually applied a voltage across these contacts, and we measured the currents across these contacts, and this gives us 5 different measured resistances which are plotted over here. Now, in order to extract the contact resistance, we need to perform a linear fit across these 5 data points. How do you perform the linear data fit? For that, we have an equation over here, as you can see. In this equation, RSH is the sheet resistance of the material. Sheet resistance is a measure of the resistance of a thin film of a material with uniform thickness. It is typically expressed in ohms per square and represents the resistance of a square of the material independent of the size of the square. R1 over here corresponds to the radius of the inner circular contact, and similarly R2 over here corresponds to the radius of the outer circular contact. In this equation, LT is the transfer length over which, or you can say it corresponds to the transfer length, which is a measure of the average distance over which current flows from the semiconductor to the metal contact. Transfer length is the distance over which the majority of the current transfers from the metal contact into the semiconductor material. It indicates how effectively the current spreads out beneath the contact, and it is crucial to determine the efficiency of current injection in the contact region. Now, so then for the fitting, we know the value of 2 pi, we know the value of the inner radius and the outer radius for each of the circular contacts. However, RSH and LT are actually 2 different unknowns. So we try out different values for these unknowns, and then the values which work for all the 5 data points, are actually the value of RSH and LT. And then how do you finally determine the contact resistance? Once we determine the value of LT and RSH, the contact resistance is simply RSH times LT square. Then what do the results actually tell us? Lower contact resistance actually indicates better quality of the metal semiconductor contacts. And then you can use these results to optimize your fabrication process, such as by improving the metal deposition contact stacks. You might have used nickel gold, or you might have used tie aluminum nickel gold, tie aluminum tie gold. You can vary the thicknesses, or you can vary materials. You might like to use platinum palladium gold for wide bandgap semiconductors. And you might like to play around with the annealing temperatures and the annealing time, etc. So these are the parameters that you can change in order to optimize your contact resistance. And by following these steps, you can effectively measure and analyze the contact resistance in semiconductor films and devices using the CTLM technique. Now let me show you a couple of examples. So for example, I performed the fitting on one of my samples. And this is actually a P-type 3-nitride film. I'm not going to go into the details of the film, otherwise it's going to take extensive amount of time. Here is the CTLM pattern for the contacts deposited on the film. I've got a spacing of 10 micrometers over here for the first contact, 20 micrometers for this one, 30 micrometers for this one, 40 micrometers for this one, and 50 micrometers for this one. The outer radii are the same. These contacts have an outer radius, or in this equation, R2 of 200 micrometers each one. So in this column over here, I mentioned the outer radius in it's given in centimeters, 0.02 centimeter, which converts to 200 micrometers for each of the 5 contacts. Similarly, if you talk about the inner radius, so for the first contact, the inner radius is 190 micrometers, 180 for the second one, 170 for the third one, 160 for the fourth one, and 150 micrometers for the fifth one. And so this column actually corresponds to R1 in this equation, and this column over here corresponds to R2 in this equation. As I discussed, we know the value of 2 pi for each of the 5 data points. We know the value of R1, we know the value of R2, etc. Now, how do we, now this column actually represents the measured resistance for each of the contacts. So for example, consider this one in which this spacing is 10 micrometers. I measured the contact resistance and it came out to be 14 ohms. I already discussed how I measure the contact resistance, so which is given over here. This one over here. So the smallest spacing, let me go back. Here I've got the smallest spacing, and as I previously mentioned there, the smallest spacing is going to result in the largest amount of current. So going back to this figure, which means that the smallest spacing corresponding to CTLM pattern will give me the largest amount of current, resulting in the least resistance for this contact. How do I measure the resistance? It's the change in voltage divided by the change in current, and I can look at these figures and make a guess, but actually I also have measured these voltages and currents. So for example, I open this file, and here if I focus on these values, so for example, at plus 5 volts my current is 1.14, and at minus 5 volts my current is minus 1.27. So the change in voltage from plus 5 to minus 5 is 10 volts, and the change in current is this one is 1.14 10 to the power minus 1, this one is 1.27 10 to the power minus 1. So I would say 0.11 plus 0.13, I would say, so that makes it 0.11 plus 0.13. That makes it 0.24. So the change in current is 0.24 and the change in voltage is 10 volts. So then my resistance is going to be 10 divided by approximately 42 ohms. Okay, so and this is going to be for the, so that actually corresponded to this one, the largest spacing over here for the 150 micrometers, 42 ohms, approximately 43 ohms. For the smallest one, I got this file, and here the change in voltage once again is 10 volts. The current at plus 5 is 0.31 and at minus 5 is 0.32. So 0.31 plus 0.32 is equal to 0.63. Now my resistance is going to be 10 divided by 0.63, so approximately 16 ohms. Here it's mentioned 14 ohms to be more exact. You can say it's 16 ohms and you can make it like 42, right? And similarly we can measure the other resistances as well. Okay, so now how do you measure the and similarly you measure the resistances for the rest of the three contacts as well. I've already got files for the rest of the three contacts as well. And so these are the measured resistances. How do you find the fit resistances? This column gives me the fitting resistances. I've calculated this resistance using this equation, but as I already mentioned that in this equation RSH and LT is unknown. So here is my sheet resistance value and here is my transfer length value. I varied these, and also let me delete this figure and let me plot it once again. So I select the inner radius and then I select the measured resistance and the fit resistance. I go to insert and go to this one. I need to adjust the axis over here. So it's running kind of like from 0.0145 to 0.02 approximately. Okay, increase the size of this figure. Okay, now the orange points correspond to the fitted data and the blue points over here correspond to the measured resistance. And what we can do is I can go to insert and I can actually draw a line. So the line corresponds to the fitted data and the blue points correspond to the measured resistance. Now I've already found the optimal values for the sheet resistance and for the transfer length as well. But what you can do is you can vary it around. For example, what happens, let me move this figure over here. What happens if I decrease the sheet resistance to 500? Okay, now it's not a good fit. What if I increase this to 600? No, still not a good fit. 700, not a great fit. 900, now it goes above the points. So a value of approximately 750 gives me a good result. You can slightly vary it to like 760, right? So you can say this gives me a good value. And also the transfer, what is the effect of the transfer length? The value for the transfer length over here right now is 0.0005 centimeter. What if I decrease it to 0.0004, for example? Not a great fit. Or if I increase it to 0.0007? No. So 0.0004 gives me a reasonable fit for, not in fact 0.0004, I gotta make it to like 0.0005. 0.0005 gives me a reasonable value for the transfer length. So now I say my sheet resistance for this film is 760 ohms per square, and my transfer length is 0.0005 centimeters. Now, but I'm more interested in measuring the contact resistance, and as already discussed, that the contact resistance is equal to sheet resistance times LT square. So what I did over here is, you can see over here in the formula, it's LT square times RSH, and it gives me a contact resistance of 1.9 into 10 to the power minus 4 ohm centimeter square, which is a really good contact resistance. Contact resistance is in the 10 to the power minus 4, 10 to the power minus 5, 10 to the power minus 6 ohm centimeter square range are really good contact resistances. Similarly, you can also measure the resistivity of this film if you know the film thickness. So resistivity is equal to the sheet resistance times the film thickness. This film had a thickness of 200 nanometers. So RSH times the film thickness in centimeters gives me the resistivity of the film, which is 1.5 10 to the power minus 2 ohm centimeter. So it has got a good contact resistance, and this film has got a good resistivity as well. So this is a sample that I've personally grown and characterized as well. I'm gonna show you another example on how to apply the contact resistance, and this is actually a paper. It's contacts applied to aluminum nitride films, and here is the data of the contacts. You can see the IV measurements over here, and you can see a resistance plotted versus gap or the spacings on the right side. The spacings in this case are 2 micrometers, 4 micrometers, 8 micrometers, 12 micrometers, and 16 micrometers. The outer radius is kept the same at 200 micrometers, and the inner radius varies according to these spacings. From the IV measurements, you can calculate the resistances. For example, look at this red curve for the 2 micrometer spacing. It is the smallest spacing, so it's going to give you the largest current, the highest current. And this current, if I focus on, for example, from 0 to 0 to 1 volts on the voltage range for the independent variable, the current is varying in the range of approximately 0 to 20 milliamps. So 1 divided by 20 milli is gonna give me a resistance. Let us measure that. It gives me a resistance of approximately 50 ohm. So you can see for the smallest spacing, the resistance is approximately 50 ohm. Similarly, you can measure resistances for the rest of the spacings as well. Then how do you perform the fitting analysis? For the fitting analysis, you can either plot, so let me increase this over here. You can either, in the paper, they have plotted resistance versus gap or the spacing, but you can also plot resistance versus the inner radius, because the inner radius is varying, right? So let me show you how it's done. This column shows the outer radius, which is fixed at 200 micrometers. Here the values are given in centimeters, and this column over here demonstrates the inner radii, which range from 1.98 10 to the power minus 2 centimeter to 1.84 10 to the power minus 2 centimeters. Or you can say it ranges from 198 to 184 micrometers, right? This column shows the resistance. It's in the paper, it's given in kilo ohms, but actually when you measure it, I think there might be some mistake. If you calculate it, it does not come out in kilo ohms, it comes out in ohms. So we can make a correction for that. 42 point this value, 61 point this value, 75 point this value, 126 ohms, and then 223 ohms. So the y-axis actually should be in the range of 40 to 250 roughly, you can say. Minimum value of 40 and maximum value of 250. Okay, so we got all the data points. Let me decrease it to, I would say, 35. Cool. And then you can vary the sheet resistance accordingly. For example, what happens when I do that? So it should be lower than that value. Okay. Getting closer and closer to the fitting now. So this gives me a reasonable fit. And now if I look at the sheet, the contact resistance and the resistivity values, The contact resistance is 1.5 10 to the power minus 6 ohms centimeter square, and the resistivity is 1.50 ohm centimeter. Now the problem is that if you make contacts to aluminum nitride films, you can, currently with the current technology available, it's not possible to achieve a sheet resistance which is that low. So the possibility is that either that I feel like this current is given in milliamps, and this resistance might actually be in kilo ohms as it is given over here. So I feel like this current, there is a slight labeling mistake. I feel like this current is in microamps corresponding to a resistance given over here in kilo ohms. So let us go back to our previous values. Cool. Now the resistances are in kilo ohms, and we have got a sheet resistance which has a value of 1.5 10 to the power of 7 ohms per square, and a transfer length which is 1 into 10 to the power minus 5 centimeters. And it corresponds to a contact resistance of 1.5 10 to the power minus 3 ohm centimeter square, and a resistivity of 1.5 into 10 to the power of 3 ohm centimeter. Now this resistivity is really high, but apparently this film has got a really small doping concentration, so the resistivity makes sense. It's still not easy to achieve this low contact resistance to aluminum nitride films, and I feel like it's a really good value for making contacts to aluminum nitride films. But I would also suggest to make further research on it. I've worked on aluminum nitride films. I've achieved both P-type and N-type doped aluminum nitride films. Aluminum nitride has a wide band gap, and it's not easy to make contacts to aluminum nitride films. So further research needs to be performed on making contacts to aluminum nitride films. Anyhow, the goal of this video was to demonstrate how to perform CTLM measurements in order to determine the contact resistance of the films, and also you can determine the resistivity of the films using a simple formula. That wraps up our guide on measuring the contact resistance using CTLM measurements. I hope you found this tutorial helpful and that it clarified the process for you. If you have any questions or need further clarification, feel free to drop them in the comments below. I love hearing from you, and I am here to help. Don't forget to give this video a thumbs up if you found it useful, and make sure to subscribe to the channel for more content like this. Hit the notification bell icon so you don't miss out on any future videos. Thanks for watching, and see you in the next one. Take care. Adios.